So I'm Andrew Perrault. I'm a postdoc with Milan Tombe. I've been working in his group for about a year. So this talk is titled Game-Focused Learning in Cooperative and Non-Cooperative Games. It's a fairly new talk, so I want this to be a kind of interactive session. There's very possibly bugs in here, so if you see something or you have questions, just ask. So the jumping off point for this is that the world is full of strategic interactions, right? Interactions between agents, like in financial markets where we have agents buying and selling goods or services. Here our conception of agent is going to be fairly broad. We're often thinking of a group of people with some kind of shared decision-making power. So you can think of, in this market setting, firms or individual traders at a firm. Application area which is near and dear to my heart is wildlife security. That's going to be the focus, one of the main focuses of this talk. So in this setting, we have a wildlife sanctuary. We have some rangers we want to use to patrol that sanctuary. And we have poachers who are going to come in and try and poach animals and sell their parts in the black market. Another common strategic interaction is this collective decision-making problem. Say we're a group and we want to take some kind of joint action together, like elect a leader, make decisions on an issue. We might use some kind of voting process or other kind of mechanism to help us make those kinds of decisions. So we're going to abstract this picture into this kind of generic interaction between agents and a mechanism or game. So here we have a three-agent game. Each of these agents is this group of orange people. The agents make decisions, and the mechanism or game returns them information and outcomes. And these outcomes are going to have some kind of associated reward payoff that the agents receive, reflecting how much they like what happened. So this is a really broad conception of what a mechanism is. You can think of this covering both the cases where a mechanism is something that's mainly human created. So if you're trading stock on an exchange, you're using rules that were engineered by people to try and make stock trading efficient, to get good global outcomes. In a security game, so when we're trying to patrol these parks with rangers, there's a lot of this mechanism which is not built by people. It's just determined by physics, the limits of how far rangers can patrol in a day, the kind of sensing equipment we can use to detect poachers. All this is in this box. In recent years, there's been a lot of interest in what AI can contribute to these kinds of problems. We can, broadly speaking, split these problems into two subclasses. So one is where we want to optimize the decision-making of one agent in the interaction. So in this wildlife security setting, we're taking the role of the ranger. We want to help them plan patrols to get a good outcome in the game to prevent poaching from happening. Another setting is we're the agent that's engineering the mechanism, right? So we're trying to design good interaction rules that result in a good outcome for the agents that are using that mechanism. Again, think market design here and what kind of trading rules people use. So there's been a lot of progress in this area from an AI perspective, just at a super high level here. One line of progress is in algorithmic game theory, what's called CS econ here, studying the computational properties of these game theoretic models, that many of which were posed by economists, but without thinking about how hard it was to compute equilibria. We developed these really powerful techniques for solving large-scale extensive form games. So a lot of the games that people play are extensive form. Think of poker, Go, StarCraft, these kinds of things. These games used to be super hard for computers to solve, and we developed these powerful techniques, counterfactual regret minimization, this combination of reinforcement learning and Monte Carlo tree search. Another lane I've sort of broadly called clever uses of optimization. So sometimes we have a game that has a super big strategy space for one of the players, right? It's a game that's played on a graph, for instance. This is a hard problem to optimize directly, Maybe the strategy space doesn't even fit in memory for some kind of optimization approach. So one idea here is the double oracle algorithm, or iterative strategy generation, connects back to some ideas in optimization. You can also think about using deep learning as an assistant in optimization. When we have an expensive function we need to evaluate, we can use some kind of deep learning surrogate, make the optimization problem easier. The challenge with applying these techniques to the real world and making the kind of advances we want to make in optimizing strategic decision making is the details of the game model are often uncertain, right? So you think of the games that people play, again, poker, chess, Go, we kind of know very, very precisely what's happening in the game. We know what our opponent wants to do. We know what a win looks like. We know what their action model is. In the real world, we often lack this information. We don't, going back to the wildlife security case, we're facing off against poachers. The poachers are responding to some economic pressures, what the value of various animal parts are in the black market, what the costs are of certain types of poaching strategies. It's really hard to know any of this stuff and just build a simulation and solve it that way. So we have to think about how we might infer these things, how we might learn them from what we can observe about the world in order to apply these really powerful decision-making techniques. And there's kind of a theoretical view of this, which is that when our model is incorrect, there are few guarantees, right? So we can have a really kind of complicated model that's wrong, and the resulting policy can have very bad outcomes if deployed in the real world. So what can we do about this? There's lots of theory around this subject. It's a pretty well thought through problem area, but the thing is, in practice, we want to apply modern techniques to these problems. So in this case, we want to do something like be able to exploit advances in machine learning and deep learning to build predictors to kind of view the latent parts of these problems from what we can observe, right? So this can really make some of these problems solvable that weren't previously solvable because we can build really good models of our adversaries this way. And this very simple approach of just putting learning together with optimization directly does provide us something we can do. It resolves this problem in some sense. Lets us apply these powerful standard techniques. But we can lose solution quality by doing this, right? If we just think about, well, we're gonna do some kind of learning to resolve the uncertainties we have, and then we'll feed this into an optimization algorithm, that's not in general going to be the best thing we can do. And this goes back to the wealth of theory on decision making under uncertainty, that's been over the last 50 or so years. So the focus of this talk is how to do this combination in an intelligent way, right? So we're in a situation we want to combine, we want to do reasoning under uncertainty, we want to use modern techniques, but we want to do better than just treating the learning and the optimization completely separately. And the first chunk of this talk is going to be on called game-focused learning of adversary behavior in security games. So it's focusing on this wildlife security setting and the techniques we developed in that area. And this is a non-cooperative setting, competition between the poachers and the rangers. And the second part is going to be on work done during my PhD. And this is on using autonomous agents to build more efficient electricity markets. This will be a shorter section, which I'll kind of do as much as I can with the time I have. The general idea here is we're taking more of that mechanism design perspective where we want to build good interaction rules that allow agents to reach a good global outcome, better than we can get with current markets. Okay. So transitioning to the wildlife security part of this talk. Does anyone have questions on kind of the motivation, the big picture? All right. So what's happening here is we're trying to protect biodiversity in wildlife reserves. So this is a wildlife sanctuary in Cambodia. You can see on the right here we have a kind of risk map we've built for this park. So this is a real problem, something we actually we have relationships with the organizations that run patrols in these places and build software to assist rangers in running patrols. The black lines on this map are roads. The blue dots are villages around the perimeter of the park. And darker red here represents our model thinks poaching is more likely to occur at the time that we queried it, and lighter red means poaching is less likely to occur. So we have a limited number of rangers we want to use to protect this huge area. We have way fewer rangers than we would need to kind of defend it completely. Set up we can set up some kind of perimeter and really control access. But no, we're just going to be able to run patrols from ranger stations and look for either poachers or evidence of poaching or snares that we can disarm, other things we can do to protect the wildlife that lives in the park. And as I alluded to earlier, the attacker's payoffs are not observed directly here. So we don't have a good kind of well-specified game model coming in. The poachers are responding to these economic pressures and costs of access to the park, and we can't generally understand what's going on here just by talking to experts. But what we do have is historical TAC data. So we have, for this kind of setting, a lot of data, years of data, where we can observe this is what the rangers did, this is the patrolling schedule that was in place, and here's where they found evidence of poaching or poachers. And we want to maximize the value of this historical attack data to plan patrols going forward. So the approach which has been taken so far is this kind of approach of separating out learning and decision making. So what we're going to do is build a predictive model of the poacher. And this predictive model is going to map from the features of the targets, which we believe are influencing the poacher's behavior, to the probability we think the poacher will attack each target. So I should say we take this big park, we discretize it into little squares, we call each square a target. Each target has associated features like how close it is to a road, so maybe that has something to do with how expensive it is to access, how close it is to the boundary of the park, maybe something like animal density estimates we have from surveys, basically all the information we can think of that might be influencing the poacher's behavior. So we build this predictive model using a standard machine learning loss function. We'll think of this as being a neural network here. And then we treat it as if it's correct, as if it's the ground truth. And then we input this into our well-developed optimization tools, and we optimize patrols. So this research is about, can we do better, right? Can we think about these two things together? And the main contributions of this work is we demonstrate that, in theory, there's a gap. So we can relate things back to what we know about decision theory and characterize how bad it can be if we generally treat these problems completely separately. We then develop what we call a game-focused approach to this problem. So this is going to let us train our predictive model with the optimization problem in the training loop. And then we test this thing empirically, so on both synthetic and on human subject data. And this is the outline of the talk. So first I'm going to give some background on the problem. I'll talk about our approach, and then our experimental results. So this is a Stackelberg security game. This is a pretty simple but powerful game theoretic model, which is widely used in these security situations for planning defender activity. I'm going to represent, so a Stackelberg security game has a set of targets T. I'm going to represent those targets as boxes. And there's going to be, so these are four different targets, and we'll use the color to represent some quantity of the target. Each target has an associated reward and penalty for the defender and the attacker. So if the attacker attacks a target and it's covered by the defender, the attacker gets a penalty. If the attacker attacks a target, it's not covered, they get a reward for a successful attack, and vice versa for the defender. The defender's action space is going to be the coverage distribution P. So this is, we can think of this here as just being the marginal probability that each target is covered by a defense resource. And the attacker is going to get to observe P, so this distribution of coverage. and then calculate their attack distribution Q. So how do they want to respond to this P and attack the targets? So this assumption about the attacker's knowledge of Q comes from this kind of, we want to be resilient against an attacker who can see into our algorithms. In the sense of, in these parks, you can visit as a non-poacher sometimes, you can observe patrols, maybe they can bribe the rangers to get access to software or something. But we're still resilient because we use randomness on the day of the patrols to confuse the attacker. In a standard SSG setting, we assume that the defender knows this Q. So we know how the attacker will react to any particular coverage that we deploy. This is this assumption that we want to relax here. We don't know the attack distribution of these poachers because they're responding to forces that we don't really know about. But we do have all this historical data. And the form of this historical data is we have targets and features that are drawn from this fixed distribution P. And then we get to see what the attacks the attacker makes against that set of targets. And a fixed historical coverage. So for that training example, here's what our coverage probability was. Okay. So that's the problem setup. I'm going to talk about how we approach this. So our first results are in theory. And these are to characterize what can happen if you use this two-stage approach. So if you train a predictive model in isolation without thinking about your decisions, what happens as you improve the predictive power of that model by reducing its loss function? And the answer here is that your defender utility doesn't necessarily go down. You can think about it intuitively so say you have a whole bunch of targets with different attacker values. We train this estimation of what the adversary's values are for each of these targets. So the adversary likes the middle this target the most, this target second most, and then the top and bottom target the least. We're going to think of this as minimizing some machine learning loss function. So we then feed this into our optimization algorithm, and we get a coverage across the targets. Now, what's happening in this coverage is these two high-value targets are driving our expected utility to a greater extent than the low-value targets. So if we make an error in estimation on the high-value targets, it's going to hurt us more than if we make an error in estimation on the low-value targets. This is where this gap comes from. You can imagine you have a model which has good global fit but bad local fit, and that model may give you a poor outcome. So what we'd like to do is something like maximize the accuracy only of the important targets, if we could figure out what those were. But we can show that in general it's hard to just hand tune a loss function in this setting. Which targets are important is going to depend on some stuff like how correlated the attacker and the defender's values for the targets are. So that motivates our game-focused approach. And here, instead of maximizing a standard or minimizing a standard loss function, we're going to maximize the surrogate for the defender's expected utility. So I guess I should say what these Qs are. So Q empirical, this is the attack distribution that we observe in the historical data. And Q hat is the estimate that we form. Okay, so this is what we'd like to do. We'll maximize this sort of simulation of our defender's expected utility on the historical data. And this is automatically going to downweight these less important targets. And we can see evidence of this happening directly in our experiments in a few slides. So in order to do this, because we want to train a deep learning model as our predictive model, we're going to need to pass gradients through this entire procedure. So pass gradients through the optimization we're performing. And this is an illustration of this in a simpler setting where we essentially can easily observe what the payoff would have been for any decision we could have made in the historical data. So we don't need to reason about this kind of what I'm going to call this challenging counterfactual question of, if we had changed our defense, how would the attacker have changed what they did? So here, our goal is just to find the shortest path between 2 points in a city. The latent state of the problem here is going to be the delays on the roads due to traffic. And the observable state will be, say, we have some sensors of local delay in a few places, and we have some other data we think will be predictive, like the time and the weather, right? So this is a toy problem. We'll build this predictive model. It'll produce predicted delays. We'll pass the predicted delays through an optimization algorithm to try and find the shortest path. And then we'll get some payoff based on how short our shortest path is. Now, our goal in this setting is to, given the data, produce the shortest path possible. And we're going to do that by just adjusting the weights of our predictive model to have the best kind of decision consequence. And this allows us, we can do training by gradient descent if we use the chain rule here to rewrite how our payoff changes with respect to our weights as the product of these three terms. So when you look at these terms, the rightmost one here, this is easy. It's just we need to figure out how the payoff our decision, our utility function would change if we change our decision. So if we change our path, how much utility do we gain? If we have a closed form statement of our utility function, this is easy to evaluate. The term on the left here, it's also easy to evaluate. This is what we get out of using modern automatic differentiation techniques. So in PyTorch or TensorFlow. The tricky term is this middle term, which is you want to figure out how the outcome of your optimization would change if you were to change your prediction of delays, right? And I'm not going to go into too much detail about how this is done in general, but suffice to say that there's a lot of work on this subject, and we're going to build off of it, and that's going to be one of the levers we use to get to this multi-agent case. Okay. So the problem I want to highlight here is this counterfactual reasoning problem. So in the previous setting, we knew if we had say we want to simulate the effects of having taken a certain path. We know what that would have actually cost us because we know what the delays were across all the roads in retrospect in the past, even if we didn't know them at the time. In this game theoretic setting, we don't know how the adversary would have reacted if we had changed our coverage, right? We don't know if the adversary is rational. We don't know what, if they're boundedly rational, we don't necessarily know what model they're using. And we somehow have to get a handle on this in order to be able to train end-to-end. I should say, one other way of approaching this problem, as a brief detour, you could just train a predictive model to produce the optimization decision directly. This is like the most direct end-to-end approach. But people have tried this, and adding the optimization structure really helps you make better decisions here. Okay, sorry. Back to counterfactuals. So the problem we have in trying to understand this counterfactual issue is that our typical data sets only contain adversary responses to a small number of defender strategies, right? So there's was a status quo patrolling strategy that was used in the past. That's all we have in our training data. We have a few different variants of it. We don't have all the points we would need to reconstruct this entire function. And in particular, we're stuck if we have a rational adversary, if we're in this case. And the reason for this is, so say we have this fixed status quo coverage. The adversary has their utilities in their heads, which we want to extract. The adversary looks at our coverage and just says, well, what's my favorite target, given this coverage? And a rational attacker just always attacks that target. So all we will observe in historical data is attacks on one target per strategy. This would make it super hard to think about, well, what would the effect of changing our coverage be? Because we have no idea whether changing our coverage by a certain amount would change the target the adversary chooses to attack. However, we can exploit the bounded rationality of our adversary. So our adversary in this case, a group of poachers, all have different preferences, right? And also all not perfect optimizers. So there's there's a wisdom of the crowds things going on. maybe on average, they're taking the best possible response to our action. But in general, there's a spread of responses. And this spread of attacks allows us to reverse engineer the relative utilities of the adversary. So they're leaking information about their relative utilities by not acting perfectly rationally. And this is kind of the first critical thing we need in order to build these counterfactuals. This doesn't get us quite all the way because we only have the adversary's responses relative to a particular defender strategy. We still don't know how to compare across different defender strategies. And given our objective to find the best strategy overall, this isn't going to get us there. And here, this gets into more technical detail that I'm going to go into. But the kind of bounded rationality models which are effective in practice are often decomposable. So essentially, they reason about the adversary's reaction to the defender's coverage separate from the inherent attractiveness of the targets. And we can exploit this decomposability to simulate the adversary's response to different defender coverages. Okay. So that's what I'm going to, I guess there's one more thing I'm going to say about our technical approach here, which is how we take derivatives through this optimization problem. There is an added challenge here that goes beyond the game theoretic issue. Existing work for doing this applies primarily to convex problems. So we can take the optimality conditions of the problem, state them as a system of equations, and then use implicit derivatives to calculate how the decision would change as the prediction changes. And the defender's optimization problem here is non-convex. The key thing is that the non-convexity is pretty weak. It's has to do with the problem globally and less about local neighborhoods of solutions. So the approach that we develop here and find to be effective, we can use a standard black box non-convex solver, and then we'll approximate these derivatives by fitting a quadratic program to the local neighborhood of whatever is returned by that solver. This works if we have smooth local neighborhoods. Okay. So talk about our experimental results here. We run experiments on both synthetic and human subject data here. Synthetic data has the advantage that we can separate the difficulty of the game and the difficulty of the learning problem. And this lets us sort of look into when our game-focused approach is doing well and when it's doing poorly. And human subject data will let us compare to kind of previous approaches to this problem directly to see how we do. Okay. And some notation we use here. So GF will be our game-focused approach. It'll be the blue line. 2S will be a standard two-stage approach, doing the learning and the reasoning separately. That's the dashed orange line. And UNIF is just assuming the attacker has the same value for all the targets. So ignoring the learning problem completely and just optimizing against some kind of conservative model of the attacker. And we'll show on the x-axis the benefit we get over UNIF. So this is like measuring the benefit of approaching this problem as a learning problem. So this is a graph from synthetic data. So you can see we get quite a bit more utility from the game-focused approach when the number of attacks is small. So our y-axis here is this utility over this conservative model. The x-axis here is a measure of the amount of data we have. So specifically, it's the number of attacks we observe per training instance. So when the amount of data increases, the two-stage approach eventually catches up to game-focused. So when your machine learning approach can exactly recreate your adversary, you don't need to think about the problems of separation anymore, because you just optimize against the real adversary at that point. But in practice, our models of the adversary aren't that good. Like, we can test this on real data, and we can see that we're in a part of the space where we can't exactly recreate the adversary. So these kind of techniques are useful. On human subject data, the story is similar, except for that our two-stage doesn't catch up to game-focused in the amount of data that we have. So it probably would if we had enough, but these experiments only recorded a certain number of human responses. Okay. So I'm going to conclude this section of the talk with two pieces of analysis comparing the game-focused approach to TwoStage. So what we've done here is we've taken a single point from one of the previous graphs, and we've split up all the different trials on the graph. So each dot here is a different instance of the problem, so a different trial. The x-axis here measures the gap between the optimal defender response and the defender response against the adversary with uniform values across all the targets. So you can view this as the benefits of learning, the potential upper bound on the benefits of learning in this problem. And the y-axis here is the extent to which game-focused is better than the two-stage approach. And what we see is that when the optimal is very close to just the uniform model, where we just treat the adversary's values for the targets as equal, we lose a little bit to two-stage. So two-stage in this case has exactly the right hypothesis. It says weight all the errors across the targets the same, right? And the defender values all the targets the same. So this is exactly the right model to have. But as the values across the targets get less uniform, the game-focused approach pulls away, right? So it can exploit this non-uniformity in values to distribute its learning errors in places that are less hurtful to the defender's learned model. The second thing we look at here is, well, what if you just look at this in terms of global accuracy? So in particular, if you look at the cross entropy on the test set of the two-stage method. So here to the right is a worse fit, to the left is a better fit. And in general, you would predict that, okay, across these instances, when two-stage fits a better model, it should get better utility relative to the game-focused approaches because the model was more predictive in that case. And we don't really see a clear pattern here. If anything, we sort of see the opposite trend, where when two-stage has a good model, that tends to be an indicator that game-focused is even better. And when when two-stage has a bad model, it's actually beating game-focused by a little bit. So this is really clear evidence of this disconnect between predictive accuracy and the defender's expected utility. Okay, so this is going to wrap up the first section of the talk. We demonstrated that these game-focused approaches can beat two-stage approaches in theory. We built one overcoming these technical challenges in the process, counterfactual estimation and non-convexity, and we tested the approach on simulated and human subject data and saw that indeed our game-focused approach is better than two-stage, at least when the amount of data is small. Okay, so I'm going to talk now a bit about electricity markets. It's a completely different setting, but the ideas are similar across the two. I'm going to try to make that connection here. So electricity markets are really complicated. They're some of the most complicated markets, I think, that are out there, at least in terms of the real kind of the fundamentals of how they operate. You have a unpredictable generation side. Generation side that has, say, renewable resources like wind and solar, which are being driven by weather patterns. And you have an unpredictable demand side, right? Depending on the weather, when it's hot, people run air conditioners. Different kinds of events can drive human demand, right? And our goal as market designers is to try and get an efficient market, right? So we want to provide electricity to people in a way that gives them high utility. So they can use electricity when they want. They can do the kinds of things with electricity that they want. But we want to do it in a way which has low social cost, right? You don't want to have to build tons of generation if it's not contributing much to the utilities of end users. And the way electricity markets are currently structured is to hide a lot of this complexity. This structure is driven, these are old structures. They're driven by technical limitations at the time. But they're also driven by some kind of fundamental attention limitations. So from an economic perspective, what leads to really efficient markets is if we pass lots of information about what's happening on the generation side of the market to consumers in the form of prices, right? So from a kind of pure economic theory perspective, something like real-time prices would be the most efficient because it causes people to change their use in reaction to what's happening on the supply side of the market. But in practice, this isn't necessarily helpful, right? It isn't necessarily the case that adding all this complexity gives you much more payoff because people have to be able to make use of this extra information in a useful way. So to kind of narrow this problem down, I'm going to focus on this sub-objective, which is we want to get lots of renewable generation sources into electricity markets in order to reduce their carbon intensity. So doing this is hard. The challenge is that renewable generation is less reliable than non-renewable generation. There are a couple ways of addressing this problem, and they're all expensive because they all involve big physical things. So one is you can just build tons more electricity production than you need at any given time. This means that even if you're very unlucky and the weather's really bad, you get a bad alignment between demand and supply, you still have enough. Another is you can build a lot of transmission lines. This means that you can sort of geographically average the outcome. So if you build enough lines, somewhere in the country they're having the right weather for renewables, and you can just route that power to where it needs to be used. Or you can build a lot of storage, right? And this is temporal averaging. You're dealing with the potential for bad luck in another way. That, well, now there will be weather in some time window. You just save that electricity from the time when there was weather it was good for renewables, and you use it in the time when the weather is bad. Okay? But there's also a fourth option, which comes from this market perspective. We can change consumer demand. There's evidence that this is indeed something that's possible. Lots of electricity usage is discretionary currently, particularly things like air conditioning and large fixed appliances. So if you ask people in surveys and they say, and you ask them in principle, are you willing to shift your electricity consumption in response to some kind of event on the generation side, they generally say yes. But this is really hard to get to happen in practice, and this is kind of major issue, major focus of this research. And the picture here is probably getting even more bright in terms of the amount of things that can be shifted. So as part of reducing the CO2 intensity of electricity generation, we want to convert all vehicles to electric vehicles, right? And this is going to create lots of shiftable electricity demand because, get home, you plug in your electric car, you might not need it to charge right away, right? You might be willing to shift some of that charging to later in the night in exchange for some kind of discount in electricity. Okay. So why is it not always successful to just pass tons of information? So why do real-time prices not give you what you'd hope from an economic perspective? So critical peak pricing is a kind of really weak version of real-time pricing. It says we're going to notify people way in advance that prices are going to go up. This is to make kind of this price information more manageable, more salient, so that people can react to it, and we end up with a more efficient market. So the way this works, you get a text message from your electricity provider who says prices are going to be 4 times their regular amount between 4 and 7 p.m. tomorrow, right? But in order for this to work, a lot of human things have to go right? You have to notice the text message, you have to be in a position to respond to it, so you have to have the right kind of automation tools you need to make this kind of response, or just do the response manually. So in practice, these are not that effective. They're only moderately effective because you have to go through this human layer. And again, people want to respond to these things. They're always more optimistic about the extent that they'll be responsive than they actually respond in practice. So this is a problem for AI, right? We can take this complicated multi-agent interaction, in this case electricity markets, and make it more efficient by introducing autonomous agents that represent the people in this interaction. So these agents, going back to our abstract view of mechanisms earlier, these agents receive price information from the generation side of the market, and they make decisions on behalf of the household they represent. So by embodying this response policy, they can overcome these attentional limits. And in order for this to work, we need two things, and the two things are what I'm going to talk about. So the first thing is we need a way of exploiting these more responsive agents to make efficient markets. So what do we actually do when we have these things? How much can we benefit? What are areas we can improve? The second thing is we need a way of learning the preferences of the consumers that these agents represent. So we need a way of establishing this link here. This is potentially really expensive because there's a ton of information here that we have to get. This is this problem of, well, if we knew everything about the game, then we could do really powerful things, but we don't know everything. We need to gather this information in the real world. Okay. So now I'm just going to talk briefly about our efforts in two parts of this problem. So the first is in making markets more efficient. So one inefficiency of current markets has to do with the incentive for consumers to be predictable. So this is a kind of cartoon view of how how markets work. We have a generator who's producing electricity. We have a consumer who's consuming it, and they're just paying a fixed rate tariff, right? So we said we're using a really simple policy here because in the current world, more complex policies don't necessarily help. We have this supplier who's getting squeezed by this problem. They buy electricity in advance from the generator, but the rate they pay depends on how late they buy it, right? So the better the model they can build of the consumer, the more efficient they can be because they can then buy electricity at a cheaper price. This is kind of a natural thing. The more the generator can plan ahead, the cheaper generation will be. But this incentive is often not passed on to consumers. This fixed rate tariff does nothing to incentivize consumers to be predictable in their consumption. So one way of addressing this problem is through some kind of prediction of use tariff, right? So imagine you have a consumer, has an agent that's representing them, so we can deal with a really complex decision-making problem. Prediction of use tariff asks each consumer to predict how much they'll consume in the next time period. And they'll be charged based both on how much they consume and how accurate their prediction was. So you can see this would be really cumbersome to do without an agent, right? Because the market is constantly asking you, what do you think you're going to consume? Okay, here's what your payoff was. What do you think you're going to consume? Here's what your payoff was. And we hypothesize that implementing this kind of prediction of use tariff, it could align incentives between consumers and generators and lead to a more efficient market. So we build off this model from the literature. So this is Robo et al.'s prediction of use games model. It's a simple cooperative game kind of implementation of this idea. So we have a set of households. Each household here is an agent in this game. Each household has a consumption profile. This is something known only to them. And this says, what is the distribution over the potential amounts of electricity I consume in the next time period? We're going to use a cooperative game model here. There's lots of research on the connection between cooperative games and markets. Essentially, this will align with many common equilibrium concepts used in economic models. So the households can form a coalition and be charged as if they were a single agent, right? This allows them to get benefits by having their consumption considered collectively. And we have a prediction of use tariff in place. So each coalition is going to predict a baseline, which is just a real number. This is the estimate of your consumption in the next time period. The key result of Robo et al. About this model is that it's a convex game. So the problem with cooperative game theoretic models, they're extremely computationally intensive. They have hard to compute solution concepts. So it's a model which is very nice if you can handle it, but in general, hard to work with computationally. The characteristic function of this convex game is convex. And that means it's a convex cooperative game which makes a lot of these computational issues go away. So you can get the benefits of this kind of computational modeling without paying all the computational cost. Okay. The problem with cooperative games, with POU games, sorry, with this prediction of use games model, is the decision that agents have to make is made, in some sense, before the game starts. It's what profile to declare to the system. Everything works out really nicely computationally with respect to a fixed set of profiles, but this choice actually turns out to be strategic. So you can imagine an agent could shift their consumption based on some levers they can pull, so maybe like the setting of their air conditioner. And these different potential shifts would yield different potential profiles. So all this stuff about, I set my air conditioner to this, here's the distribution of what the weather could be, this yields a consumption profile, some distribution. And this is a game theoretic question. So the best profile to choose is dependent on what the other agents report. And so what our model does is we build this profile choice into the game itself. So now agents can have a set of profiles. They can choose between them and choose what to report. But we show critically that this extension remains convex. So we keep all the benefits of this powerful cooperative game theoretic model. It raises some incentive issues, and we do some work to resolve them, but I'm not going to talk about that. And it turns out that these MPOU games address a key weakness of prediction of use games. So the challenge faced by agents in prediction of use games is they have no idea what the other agents are going to do. So they need to sort of guess which profile to report ahead of time. This relates back to the bigger theme of the talk. They're making a decision with incomplete information. This x-axis of this graph essentially states how little information they receive about the other agents, so how bad their guess will be. The y-axis, this is the amount of social welfare, so this is a measure of the global efficiency of the market. And the blue line is the performance of the prediction of use games model. The red line is the performance of our multiple profile model. So high level here, multiple profile prediction of use games are much better at coordinating agent demand than prediction of use games. And we can also see that we get some benefit over a fixed rate tariff here through that better alignment of incentives. So this is not the only aspect of electricity markets that autonomous agents could improve, but this is one kind of narrow issue which you can study separately, where we can see some pretty serious benefits to this kind of approach. Okay, so the second and last thing I'm going to talk about here is the problem of how we actually build these autonomous agents. So the standard approach to this would be to use a combination of machine learning and preference elicitation. So you can use machine learning by looking at the historical data of the household you're trying to represent. You can say, in all these different situations, here's what they did. I can use this to try and build a model of the household. The problem with this in general is that introducing the agent is going to change the user's behavior. So you think, it's very rare that you adjust your HVAC while you're asleep, because that's just something which is never worth it for you to do. But if you had an autonomous agent that could do it for you, you might want to do it. So preference elicitation allows you to query the user about these hypothetical situations and improve over what they've done in the past rather than just reproduce it. The standard approach to this is a two-stage approach. You just do everything up front, right? You use machine learning to learn a good model. You fill in the gaps with preference elicitation. Then you feed that into your optimization problem. And the problem with this standard approach is that it front loads all the effort, right? I have to learn about your reaction to every possible hypothetical situation if I want to make good decisions on your behalf. So this is a ton we have to cover up front, and we don't get any benefit until those situations come up. So there's a huge cost. And the other thing is I have to ask you to answer questions about stuff you don't necessarily understand on a rational level, right? I have to ask you to respond to questions about really distant situations from the current one you're in, to say things like, if this were the temperature and this were the time of day and this is what you were doing, what would you be willing to decrease the temperature of your apartment by 1 degree for an hour? And it's really hard for most people to answer those kind of questions. So our approach to this we call experiential elicitation. And the idea here is to intertwine the preference elicitation problem and the decision making of the system. So in a nutshell, we want to make queries when the system is uncertain about what decision to make in the near future. So if the system says, well, I don't know if you want to do X or Y, and there's a big difference in potential payoffs for these things, okay, it's time to ask you a question about this. And it also allows us to account for this state-based query uncertainty. So basically, this is accounting for if I ask you a really distant hypothetical, it might be much harder for you to give a good answer to that. We can build that directly into the model and think about the cost of the query and maybe postpone asking that until a more opportune moment arises. And the result of this is better performance. So here on this graph, we have the time axis of our sequential decision-making problem. So here we're simulating a household. We have this agent making decisions on behalf of the household. And we have 3 lines here. The orange line is using this estimation of query value. So it's postponing queries until they're relevant and not asking them when they're not, and using this to inform the query strategy. And the result of this is receiving a much higher reward than the other strategies which do all this querying just all the time. And so this result, so what we get here is that these queries that are not immediately valuable are delayed until they are. Okay. So that's it. The central idea I want to state here, we want to consider interactions between the learning and decision-making problem to make systems that make good decisions under real-world uncertainty. And we want to do this in a way that lets us use these modern advances in decision-making and learning, right? So we don't want to go completely back to old methods that deal with these problems optimally, but don't let us exploit these modern computational advances. So here, this was often, in the first part of the talk, we were thinking about deep learning on the learning side and modern optimization approaches on the optimization side. Okay, thank you very much for listening.
So I have a question for the first part. So we talk about doing the gradient descent, calculate the derivative.
Mm-hmm.
I'm just wondering, do you have any comments on in what scenarios you may stuck with a local optimal solution, and how do you know that, and whether the compensation of multiple derivatives makes that more easily to reach to a local optimal, or it's actually going to avoid that for most?
Yeah. I guess there's kind of 2 different types of local optima in this problem. One is the local optima in the forward pass. So does your optimization problem give you the global optima given your prediction, right? And that case we can avoid because we use a black box non-convex solver. So in general, if our solver is good enough, we will get the global optima there. Here, this is sort of using the techniques that are out there to get good outcomes. The other kind of local optima is, can we get stuck in a local optima of the weights of the learning problem? That one is harder. In this case, we generally think that we aren't because of the structure of the defender's utility function, the kind of weak non-convexity that we see. But it's, possible. It's definitely possible in general. I don't know if the combination of derivatives makes it easier or harder for that to happen.
Previous scenario, there's a lot of uncertainty with regards to how much information you can actually collect, right?
So I mean, I don't know if this is along the lines of what you're thinking of. There are issues about, a ranger, when they're patrolling, they're not necessarily providing the same amount of search effort everywhere. So you might imagine that a ranger, driving their motorcycles through a certain area, that's not the same as walking through it and searching very carefully for signs of poaching. That is a kind of an interesting problem for these kinds of models. We don't In this current work, we don't do anything, what I presented, we don't do anything very sophisticated to deal with it. In the two-stage approaches, we have developed pretty sophisticated approaches to that kind of issue. Essentially, weighting training examples that are reflective of less effort, less than training examples that reflect lots of patrol effort.